Welcome back to ECE 340. This is a review session for exam number 1. Hopefully it is recording. We'll find out, I guess, in a little bit. The process you should already be familiar with. It's one sheet of notes front and back, and a calculator and something to write with. The list of topics is already on D2L, but just to get us thinking about what you're responsible for, this is a brief list. It may not be inclusive of everything, but you should be able to sketch waveforms. You should be able to write down expressions for waveforms from plots, and that's in terms of unit steps, ramps, and sines and cosines. I won't really ask you to try to figure out what a functional form is other than sines and cosines, ramps, or constants. Energy and power signals, being able to determine those. You should be able to write state space equations from an RLC circuit. A particular system's characteristic, whether it's linear, nonlinear, whether it's time invariant, whether it's time varying, whether it's causal or non-causal, the system order, whether it's dynamic or instantaneous, all of that you should be okay to do for the exam. Given a collection of waveforms, you should be able to figure out what is the frequency content in this particular sinusoidal signal, and that can include a DC waveform. So the frequency there would be 0, for example. Impulse response, you should be able to know what that means, or really what is the structure of the impulse response. So if I give you a transfer function, can you basically tell me what the impulse response structure would look like? What are the terms that are present? What are the decay rates or amplifications? What are the frequencies that are present, or the damped frequencies of oscillation? Can you find a transfer function given an RLC circuit? From that, can you identify poles and zeros? And obviously then in that transfer function, the poles of that determine whether or not your system is bounded input, bounded output stable. Floor is open if you have a particular question. If not, I can just start running through some topics that I have prepared in case there were no specific questions now. I don't know, I didn't remember. Energy and power and signals. So is that what you're interested in? Or determining whether or not a signal is an energy signal or a power signal. If you have, for example, let's say somebody gave you the following waveform. They said, here's x of t, a function of time, and then they said, well, it's going to start at 4 and maybe it finishes at 6. And then maybe they tell you this looks like t minus 4 squared, where it's non-zero. And now they ask you, is this an energy signal? Is it a power signal? Is it neither? And what would you be inclined to say? Or are you inclined to say anything at this point? You need to be able to define that or identify that by the time of the exam. And when we're talking power, and again, these are generic energy and power. The units may not be precise, but we're basically saying the integral of the absolute value squared is going to give us the energy when we integrate from minus infinity to plus infinity. And the average power, then we divide out that time interval that we're integrating with respect to. In this particular case, what is this waveform? Can you tell by inspection? It's an energy, isn't it? It's bounded. And if you computed the energy in this expression, it would give you a bounded value. And since it gives you a bounded numerical value, then that would be an energy signal. Now, so you could say, okay, this is an energy signal and it's not a power signal, because if we looked at this over all time, over the time horizon, and divide by an infinite amount of time, the power in that signal is zero, the average power. So it's not a power signal. Now, if somebody said, give me the energy in that signal, and you said, oh, that looks kind of ugly because now I have to do this. Let's say energy in x is now this interval or integral from minus infinity to infinity of the magnitude of x of t squared dt. And now I need to look at t minus 4 squared squared. But if you think just a little bit, you can say, well, it really doesn't matter if it's shifted over 4 or not. The energy in a waveform that was shifted towards the origin would have the same amount of energy as this waveform, meaning the following signal, x bar of t, has the same energy as x of t did. And if you need the numerical value for the energy in x of t, you could compute the energy in x bar of t and get the same answer. Likewise, if somebody said, what about the energy content in this signal, which is, let's say this is minus x bar of t. What can you say about that signal's energy? It's the same. So now you could, if it was easier, or if you like to work with x bar of t, it's the same as minus x bar of t in terms of its energy. And now if you really wanted to find, let's say we wanted to find the energy in x bar, now we would, the integral is over all time, but it's only non-zero from 0 to 2 in this particular case. And now we would take whatever x bar of t was, but that was simply as a function of time, t squared. But we need to square that to get the energy, and we integrate that with respect to time. And now we have this integral from 0 to 2 of t to the 4th dt. And that would be then this 1/5 t to the 5 evaluated from 0 to 2. Or it's now 1/5 times 2 to the 5th, which is 32, isn't it? So you now have 2 to the 5th minus 0 to the 5th, or you now have 32 over 5 joules. And that's the energy in that original waveform, x of t. So now this particular signal, if we wanted the power in x of t, now we are looking at, is that the question? So if you looked at the power in x of t, this is now the limit as t marches off to infinity of 1 over t integral from minus t over 2 to t over 2 x of t quantity squared dt. But now in terms of what piece of that integral is non-zero, it's not very big, is it? We could keep this limit, which we need to, for the average power. We say the limit as t goes to infinity is 1 over t, But now we still only are really going between 0 and 2 for the non-zero piece of that signal's content. And we now have this t to the fourth again, dt. But when we divide by infinite, this is now going to give us a power of 0. And that's not a power signal then, it's an energy signal. So a power signal looks like it could be as simple as some sine or cosine that's infinite in extent or in duration. This could be a power signal. Let's say y of t is now a power signal. And you could then, if it's periodic, then you just have to look at it for one period. If it's not periodic, then that's when you need to let time go to infinity, and you basically average the area underneath that y squared curve. And you would have to be given some information on that waveform in order to do that integral. Well, if it's not periodic, then it really is not, you can't really force a period on it, but you could maybe look at a large horizon and say, okay, what's the average here? And then you could maybe change that interval and say, oh, my average really hasn't changed much, so that must be the average power. That's what you could do practically. On an exam, the waveform would probably be periodic, and you would need to then find the period of that waveform and divide just by that period. Is that clear? So in this case, if it was periodic, let's say it was periodic, then I would say, okay, here is my time interval. And I would say this is my period, capital T. Let me just make sure it's different from the variable t. Let me just say that's T1. And now I would integrate, and maybe this particular time is A1, and this particular time is A sub 2. And what I would do is I would say, okay, the power in y is 1 over T1. I have to divide by the period that I'm integrating with over. Now I'm integrating from A1 to A sub 2 of y squared of t dt. And now I would have to be told functionally what is y so that I could integrate it. But it, so now the answer would be a generic unit of watts. So this would then be some value in watts. So if y of t, let's say that's a cosine of 50 pi t. What's the power in that y of t? And this is true, let's say, for all time. Maybe I should say y bar. What do we know about that waveform? So now if we know that we have a cosine, what have we learned, I hope, in one of the sections of the book? For any frequency, what's the power? It's the amplitude squared divided by 2. So if you do this generically for any periodic waveform, you will find that the power ends up being the amplitude squared divided by 2. And if you had multiple frequencies in that waveform, you could just look at each of those because the cosine and sine would be orthogonal, and you could just just do it individually for each sinusoidal piece that's making up your y bar. Does that help? Now, if your waveform had an unbounded power, and an unbounded energy, then it's neither an energy or a power signal. And you would say it's not an energy signal and it's not a power signal. And that could be something that's growing unbounded with time. Let's say z of t is equal to t. That's neither an energy signal nor a power signal. Question? Pardon? Is that what you said? So now e to the t, what would you guys think on that? Is that a energy signal, a power signal? What is it? That's neither one, is it? Because it's growing with time. It's not bounded. And even if you divide out the time, this is growing faster than that denominator factor. Question? Oh, okay. So I was getting hung up on just having a step, but you were you were switching on an exponential waveform. So now you're saying, let's say that we had a w of t equal to e to the minus t, and let's say u of t. Now that is a energy signal because you can find the area underneath that energy integrals waveform. You could integrate all the way to infinity. It's going to vanish. So that endpoint or limit is okay. Question? Yes. So you don't have to go through a lot of the machinery if you can show so the question was, I believe, if you had a collection of sines and cosines and you were trying to find the average power in that, can you set up the expressions and show how the different pieces fit together and not have to go through all the details in the derivation? And that's fine. Yes. Well, you could do that. In practice, somebody might say, here's a waveform, find its average power, and they may be only interested in it while it's on for a week or for 10 seconds, and they may say, what's the average power in this waveform when it's only on for 10 seconds, and you could find that. But in this class, we're doing the ideal or the theoretical definition of energy and power. So we won't allow that kind of situation to occur. Let's move on to something else because your whole exam won't be on power and energy, I don't believe. So we could, if, what question do you have? So now if I gave you, let me see if I have an example that might, suppose that I said, here is a differential equation, and one of the questions might be, what is the characteristic equation? And then you can figure out the structure from that in terms of the impulse response. Meaning, if I said, here's a differential equation, let's say it's the second derivative with respect to time of y of t, plus 8 d by dt of y of t plus, let's say, 41 y of t is equal to 3 dx dt plus 5 x of t. That's, let's say, is the governing equation of a system. It's the input and output relationship for a system. You could put this into our, what do I want to say, this operator notation that we talked about earlier. We could say, oh, d, there's d squared, plus 8d plus 41, and that's now operating on y of t, and that's now equal to 3d plus 5 operating on x of t. That's now the operator notation, and it's cleaner or easier to maybe look at. This immediately can be taken into the frequency domain. Now we're essentially replacing the d's with s's, and we now have an s squared plus 8s plus 41 times y of s is equal to 3s plus 5 x of s. If I'm interested in the characteristic equation, is anything here going to help me? I've already really identified the characteristic polynomial, haven't I? Here is that expression in S, that polynomial in S, that's multiplying y of s. Here is our characteristic polynomial, which if I set it equal to 0 will give me the characteristic equation. Characteristic equation then is this s squared plus 8s plus 41 equaling 0, where we might even call that q of s for the characteristic polynomial. And now we need to find the roots of that. And I will probably give you, I could give you an 8th order polynomial, but I would probably factor it into pieces that are 2nd order. You need to be able to do the quadratic formula. But those pieces may not result in complex roots. They may be 2 real roots, but I may not factor them down that far. Is that clear? I could give you s plus 1 times s plus 2 multiplied out, and it's not necessarily going to yield complex conjugate roots. It will just give you a root of -1 and -2. In this case, though, what kind of roots do we have? If you look at this, you'll see that it's s squared plus 8s plus 16, and then 41 minus 16 is 25, which is a nice number. So this actually looks like that. And from this, you can find if you could see that. If you couldn't, just plug it into the characteristic polynomial and the roots will jump out at you. You now have roots at -4 plus and minus j5. Now that you know that, now you can tell others what the structure of the impulse response is, or what the structure of the zero input response is. What's the structure of those two responses going to be if we know we have roots at -4 plus and minus j5? There's a question. What I was doing was I was looking really at this guy, and I was taking half of it. I was really looking to see if I could complete the square. Meaning if I know that I had that 8 there, if I took an s plus 4 and squared it, I would get an s squared plus 2 times 4s plus 4 squared is 16. And now this is giving me this s squared plus 8s plus 16, but I need something a little bit more to give me the 41, and that's where I added in the additional plus 25. And that is nice because it can be 5 squared. So that's where that's coming from. Is that what you were asking? But if you don't see that, you can plug that into the quadratic formula, and out should pop these two roots, minus 4 plus and minus j5. Now that you have those 4 roots, or 2 roots, what's the structure of your zero input response? Or I could ask you, what are the characteristic modes? That's just e to the root t. In this case, it's minus 4 plus j5t and e to the minus 4 minus j5t. Those are our characteristic modes. And now you can see, I hope, how the structure of your zero input or impulse response fall out of that. You have an e to the minus 4t, that's the decay, and then you have these oscillating pieces, e to the j5t and e to the minus j5t, and that can correspond to sines and cosines of those frequencies. Meaning you can now say, oh, the zero input response could be y sub 0 of t is some unknown constant. I'm not asking you to find that. Alpha e to the minus 4t cosine of 5t plus a beta e to the minus 4t sine of 5t. And that could be the structure of your zero input response. Bless you. Does that help answer your question on impulse response? What did I say? The characteristic modes will be determined by the roots of your characteristic equation. And you then have, if you wanted to think about that, if you now said, oh, I have a root S1, which is minus 2 plus J3, then usually you might say this is now minus sigma plus J omega sub D. This is the amount of damping that you have, and this omega sub D is the damped oscillation frequency, or the damped frequency. So the imaginary piece will give you the frequency of oscillation, and the real piece gives you your either damping or unbounded exponential behavior. Question?
On the right side of the equation, there was a 3 sigma plus 5.
Oh, way back here. So now here is a 3s plus 5. So now what does that have anything, does that influence the structure of your zero input response or or impulse response? Does it influence the structure? No, it will change the coefficients of those pieces, those terms, but the main structure of your response are not impacted by that. That s plus 5 is important. If I now ask you to find the transfer function, now I can't remember what I had, but I had something like s squared plus, was it 8s plus 41? Y of s is equal to s plus 5x of s, or was it something, was it 3s plus 5? Three s plus 5. Now if I ask you for the transfer function, that expression is important. Now you're looking at y of s over x of s is now this 3s plus 5 over s squared plus 8s plus 41. But if I ask you for the structure of the impulse response, h of t would just be determined by the roots of that denominator. And this you could say, oh, that's a1 e to the minus 4t cosine of 5t plus an a sub 2 e to the minus 4t sine of 5t. And that would be the structure of your impulse response. Now, if you really had to get the actual impulse response, you would have to account for that 3s plus 5, and that would influence your partial fraction expansion coefficients. But that's not what we're dealing with in this first exam. We're not worrying so much about inverse Laplace transforming to that level of detail. You can have the whole table. For this one, you need to be able to essentially, the question I think was how many transform pairs should we write down? And you could go into chapter 4, I think it's table 4.1, just to get used to that table, and it has the Laplace transform pairs on it, and you could make that a part of your table or sheet of notes, and I may give that to you for the second exam or allow that in addition to your sheets of notes. But for this exam, you really need to know if you have complex conjugate poles, how does that translate into structure? If you have real poles, how does that translate? So if you had a, let's say you had s plus 1 times s plus 2 times s plus 3 squared plus 4 squared all times y of s equals some x of s. Now your zero input response or your impulse response structure would be, let's say, b1 e to the minus t plus a b2 e to the minus 2t plus a b sub 3 e to the minus 3t cosine of 4t plus b sub 4 e to the minus 3t sine of 4t. And you can write that down by inspection, essentially. That's what I'm wanting you to be able to do for this exam. Those are the inverse Laplace transform pairs that I want you to be comfortable with. Does that help answer your question? If you had something like y of s is equal to, let's say, 2 over s, so the 1 over s gives you a constant. That's the unit step. And this is for the one side of the Laplace transform. This u of t is really just a switch. So you could write, I'm not sure if I understand. So this is for t greater than or equal to 0. Or you could have said y of t is now 2 for t greater than or equal to 0 there also. So now if you have a differential equation, let me give just an example from an earlier exam just so that I have something to play with. Let's say that somebody gives you the following. They say, okay, here's the third derivative of y with respect to time plus 3 dy of t minus 1 dt plus 2 times the sine of 4t y of t, running out of room, minus 2 integral of y of tau d tau, let's say that's from 0 to t, minus 5 dx of t dt. Is that what you're asking? Now, what kind of characteristics or properties does this differential equation possess? You don't have to find the characteristic equation, especially if the indices on your time or on your variables are different. In this case, there is a delay there. So now if you tried to Laplace transform this, you would end up with irrational pieces in your Laplace transform because of this delay or advance in your argument. Now what you're wanting to do is just look at this in general and see, is it linear? Is it nonlinear? Is it time invariant? Is it time varying? Is it causal? Is it dynamic? Is it instantaneous? What's the system order? Those are the kinds of questions you need to be asking with respect to this equation. In this particular problem, when you're looking for something that's linear, I think that was your first question, is this system linear? Then you're looking to see, do I have y or its derivatives or x multiplying each other? Do I have product terms? Or do I have some nonlinear operation on y or its derivatives or x and its derivatives? Do I have something like sine of y of t? Is that there? Do I have something like dy of t dt times x of t? Is that there? These would all be nonlinear terms which would cause your whole system to be nonlinear. In this green equation, do I have any nonlinear terms? No. So this particular green expression is linear. So now what we're not doing is we really are taking this in the generic sense of the integral. I think the question was, what happens if you now added a constant? If somebody added a constant into this relationship, then you would have a nonlinear system. But this particular y now is, what I should do is just do this as far as a indefinite integral. And then we won't have any problems with that constant floating around. Pardon? So if I added in a piece that I said plus 6, then I have a nonlinear equation. Because this doesn't satisfy that. If I picked an x1, that gives rise to a y1, and I picked an x2, and that gives rise to a y2, their linear combination, this 6 is going to mess that up. So that's not there if we have a linear expression. So is this time invariant or time varying? What makes it time varying? This coefficient right there makes it time varying. So this piece gives us the time varying piece. So it's linear, time varying. Is it causal? It has something to do with the t minus 1. And now what I would probably do is I would make the argument of that term 0. That now says, oh, the derivative of y at 0, now do I have anything forcing that? Is it all in the past, or is there some future terms forcing that? Meaning if I now said, if I look at that piece, I have y prime of 0, so I let t equal to 1, didn't I? And if I go back up here, I have y of 1. My outputs I really don't care about for causality, but I look now at my input, and now that's, I have this dot, dot, dot minus 5 dx of t, so that's now dx of 1 dt equaling 0. And does that help me answer this question of causality? Now it's saying that my output at its derivative at the present time depends on a future input, an input at time t equal 1. So this is actually a non-causal system. I plugged in 1 for t just to make this argument nice. You could plug in any value you might want. So now what you want is you want your present outputs or their derivatives to not depend on future inputs. You don't want future inputs influencing present values of your output. So now you would have an earlier output's derivative depending on the present value of the input. So it's, I think you're making it too hard. So just draw the line and say, okay, now I have an output at time t equal minus 1. Does that depend on anything in the future relative to t equal minus 1? And in that case, it would. If you plugged in t equal to 0, then you would have y prime of minus 1 and some other terms, but now you would have minus 5 dx of 0 dt equaling 0. And now you have an input in the future relative to this output driving this output. And that's the same relationship that you had up here. Does that make sense? So it really doesn't matter what you pick for t, just as long as you kind of think through what you've got. So this says that you now have a non-causal system. Question? Correct. So there's a distinction. The question, I think, was we need to make sure and be clear on whether we have squaring or cubing of a variable or second or third derivatives, right? So there is a clear distinction. You can have a very high order derivative on your output, and that still results in your system being linear. That doesn't make it nonlinear. It's only if you have product terms or nonlinear operations on inputs or outputs that you get the nonlinearity. Question? No. So the question was, am I going to be expecting proof by definition of linearity? No. You just have to basically say, here is the term that's causing the nonlinearity. And if forced to do it, you would be able to show me that. But on the test, you're not going to have time to show, here's x1 and y1, here's x2 and y2, and boom, 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 boom. So don't worry about showing it, but just identify the piece that's causing, or pieces that, you just have to identify one piece that causes the nonlinearity. Question?
Yeah, we have to define intervals and convolution.
No, you won't be responsible for convolution on this exam. What else did I have? I had some questions on sketching waveforms, or, pardon? Oh, the order of this. Oh, I was going to say order in the court. I didn't know what we were doing here. So what is the order of this differential equation? It depends on the output, doesn't it? If you didn't have this piece, it'd be easier. But now that you have that piece, that throws a little bit of a twist on it. But what you can do is you can now say, well, you know what, that's clouding things up. So why don't I just define a new variable? Why don't I define z to be the integral of y? Then z prime is going to be y. Z double prime is going to be y prime. Z triple prime is going to be y double prime. And I just keep going until I run out of what y was. And y was triple primed, wasn't it? We had the third derivative of y. So we have the fourth derivative of z is equal to the third derivative. And now I can go back up here and I can say, oh, I can replace this third derivative of y with z to the fourth. Now I can rewrite that expression as z to the fourth plus whatever mess it was, 3 z to the first, wasn't it? T minus 1. Oh, but this is z. So that was y prime. So this is z squared. Am I okay? Then I had plus 2 sine of something, 4t, y, but y is z prime of t. So this, oh, I'm doing pretty poor on this, aren't I? So this should be, now I'm going to really get you confused on squaring and not squaring. Is that better? So z shouldn't be squared. It's the second derivative of z. What else do we have? What? It just matters on the output. And then we have minus the integral of y, which we called z, and then that's equal to these x pieces over here. And the key thing is I've now figured out that my system is fourth order, effectively. Yes, so now there's effectively 4 energy storage devices in that system that gave rise to that differential integral relationship. Do we want to do a state space? Let's say that we had suppose somebody gave you the following. They said, here's a voltage source, let's call it x1 of t. Here's an R1. Here's a capacitor. Here's a resistor. Here's another capacitor. Oh, here's an inductor. Here's a current source. The restroom is just outside the door. So here's R1, R2, let's say this is C1, C2, L, and let's say this is X sub 2. Uh, so this is I didn't hear that last comment. I don't know if it was, but it's something that I'm just getting you thinking about in terms of you should look at the old exams and make sure that you're comfortable and really what you want to be able to do is think your way through it. So don't get too excited too quick. But if I ask you now, what's the, and maybe I need to give you some outputs. Suppose that I tell you there is an output, let's say here is an output Y1, a current, and maybe this is an output Y sub 2. Let's say that's all we have for outputs. But now that we have that, can you tell me anything? And I've told students in previous semesters, if you really get hung up, at least look for giving me the dimensions of the different matrices or the state vector and the input and the output vector dimensions. That will give you some credit. In this case, if I said, how many inputs are there? 2. So what does that say about the B matrix? B is the input matrix. What does that tell you about B? All you've learned so far, if you have two inputs, is you have two columns in B. You don't necessarily know how tall it is just yet. How tall it is determined by how many state variables you have, and how many state variables do you have in this system, or how many energy storage devices do you have? 3. So the input matrix B is 3 by 2. And what are some of these state variables? Can you now label the state variables in this diagram or in this circuit? We need voltages on capacitors, don't we? So this we could say, let's say that's Q1. Let's say this is now Q sub 2. And you can decide which direction you want that inductor current to go, but let's say that's Q sub 3. Now what do we do? Well, you may have to do a combination of KVL and KCL. You can't really do a KVL here, can you, because of that guy? You don't know what the voltage drop on that current source is. You could do a KVL here. You could maybe do a KCL here at the lower node. So let's just try that. Let's see if we can just get started. Let's see if we can just start. Let's call that B1. Let's do a KCL at B1. I have an X2 coming in to the node, so I could say X sub 2 of T is coming in. What else do I know? You have the current from that capacitor coming down, so that's coming in also, isn't it? And you can write that, express that in terms of that state variable Q sub 1. You have plus C sub 1 Q sub 1 prime of T. Is that okay? What? You can do dots or primes, whatever you feel comfortable. As long as you do Q's, then not I's, then it's pretty clear, hopefully. But if you were using I's somewhere, then probably primes are better. That's maybe our alarm. Now what do we need? So now in this equation, what do we want? We want x's and q's, don't we? We really don't want y's because y's are outputs. If we write a y, then we have to re-express that y in terms of inputs and state variables. But you're right, we might like to know maybe a current coming in here, which is minus y1. If we said the sum of all of these currents coming into B1 have to sum to 0. What's the current coming this direction? Well, that's just the current going through R1, but we have that in terms of Q1 and X1, don't we? We can say Q sub 1 minus X sub 1 divided by R1 is the current coming into that node from the left. You now have to figure out what's a good reference node, and the reference node here is, well, we really haven't established one, but for that particular point, we have this as your reference node as B sub 1. Meaning we now have, we could say this is now plus Q sub 1 of t minus x1 of t. That gives us now the drop across R1 divided by R1, and all of that is equal to 0, and that's basically the first equation. And that gives us now a Q1 dot equation. We could do something similar over here. At B sub 2, we could write a KCL equation. For this, we now have Q sub 3 coming in. We have C sub 2 dQ sub 2 coming in, and we have X sub 2 leaving. Is that okay? So we have Q sub 3 of t plus C sub 2 Q sub 2 dot of t equaling X sub 2 of t. And that's another equation. And the last one we could now write from the KVL around that left mesh. If we start in the lower left-hand corner, we have minus x1 of t plus, okay, we may not be able to because we can't really establish a reference node very easily. But I guess we probably can. But then we're going to get a couple of Q primes in there. We just have to remove one of those, but that's okay. So I think the comment was, can we write a KCL here? And that's okay. It's just that we would end up with a Q1 prime and a Q2 prime, and we would want to get rid of one of those to give us all three equations that we need. If we now, well, I guess we'll do the same thing here too, essentially. If we, how do I want to do this? So if we did what you had suggested, we would have an X, let's say that we now did the following. We would have a current coming in from the left, which would be X1 of t minus Q1 of t over R1. Then we would have a current down through that first capacitor, plus C1 Q1 prime of t plus Q sub 3. Whoops. Those are all leaving, so I need to change this, don't I? So this was coming in from the left, x1 minus q1 over r1, and now I'm having everything else leave. So I really wouldn't want to do the left mesh actually because I couldn't. So I would probably, I'm not doing that right now. I'm actually doing KCL at top node plus Q sub 3 plus C sub 2 Q sub 2 dot of t. Now I'm wondering, I could now, this, if you look at it, is the same thing as those two top equations that I just wrote. So I didn't get anything new out of this. So everybody's, I don't know if you see that or not, but if you look at this, this is x sub 2. And if you look at the very first equation that we wrote, essentially that's what we have here now in terms of x sub 2. So we haven't bought ourselves a new equation. This is just another, this is not independent of b1 and b sub 2. So what we should do is we can now come over here and write a KVL around this branch because we need a Q sub 3 dot equation. Let's now write, so this is nothing new, but if we do a KVL at right mesh, now let's say that we start down at b sub 2 and go up. Then we have a minus q sub 2 plus, maybe that's the wrong direction. The voltage drop from right to left on R sub 2 is minus this current going down through there. We have that current as C sub 2 Q sub 2 dot, right? So we're going against that. So this is now minus R sub 2 C sub 2 Q sub 2 dot of t. And then we need to do plus L di dt, and that's Q sub 3. So we have plus L Q sub 3 dot of t is equal to 0. Now we do have an expression for that somewhere. That's up here, and we can now use that to replace that piece, and we have a Q sub 3 dot equation. Those are now your state equations. You will then have a Q1 dot, a Q2 dot, and a Q3 dot. You now need to find your output equations. But y sub 1 we just wrote essentially earlier, and y sub 2 is Q sub 2. So we could now say that y1 is that current going from left to right. That's x1 minus q1 over r1. and y sub 2 of t is just q sub 2 of t. No, the question was, is there going to be a lot of matrix stuff? I might have you put this in a matrix form, but I'm not going to have you playing with matrices on this exam, other than just putting the values or the expressions into the matrices. Is that what you were asking? Yes, I would. So now if we look at this, let's just see what we have. We have a Q1 dot. We'll need to divide everything by C1 and push everything else on the other side. So we have this term Q1 over R1, and they'll have a C1 with it with a minus sign. This is now minus 1 over R1 C1 Q1 of T. Did I pick up the right piece? I've now picked this piece up on the other side. I also have a couple of input terms. I have a plus x sub 1 that's the far right hand term pushed to the other side, and then I have a minus x sub 2 with just a C1 underneath it. That's now my first state equation, and that would form the first row of my A matrix and the first row of my B matrix. And we can do that in just a minute, but let me get the other couple of equations. Now I have a Q2 dot. I'll divide everything by C2 and push everything to the other side. I now have a Q2 dot is equal to a minus 1 over C2 Q sub 3 plus 1 over C sub 2 X sub 2. Is that right? And now I have my last equation right there, and I'm going to solve that for Q sub 3 dot, so I'll divide everything by L, and I have Q sub 3 dot is 1 over L times whatever I end up with. Let me say I have a Q sub 2, then I have a C sub 2 Q sub 2 dot, but that's buried in this equation right here, and that's scaled by R sub 2, and is that on the other side? So I now have a plus R sub 2 times a minus Q sub 3 plus X sub 2. Is that okay? That gives me my C sub 2 Q sub 2 prime. Oh, and that's all I have to play with. So this now becomes 1 over L Q sub 2 minus R sub 2 over L Q sub 3 plus R sub 2 over L X sub 2. And I can now put those into the matrices if I want. My A matrix, what's the size of my A matrix? It's 3 rows tall and 3 columns wide. So I now have a minus 1 over R1 C1 and 0, 0. How big was my B matrix? That's 3 rows tall and 2 columns wide. And I had an x1 coefficient, 1 over r1c1, and an x sub 2 coefficient, wherever I'm, minus 1 over c1. Is everybody following that? Then my Q2 dot equation gives me my next one, which is 1 over C2 here, 0 there, and was it a minus 1 over C2 there, and I didn't have any x's in, oops. That's a 0, and I had something scaling the second input, didn't I? 1 over C2. That's now my second row in both A and B. And my last row, I can write down from this equation, it's 1 over L, and then it's minus R2 over L, and then I have R sub 2 over L and a 0. And the output equations follow from the Y1 and Y2. What's the top row of C look like? Then do I have anything in my D matrix? Now I'm asking, are there any x's in my output equations? And there is one. There's an x sub 1. And its factor or scale, its coefficient is 1 over r sub 1. Then the second row is just q sub 2. And those are now my matrices for the A, B, C, and D. If I didn't make any mistakes. Questions on that? That's probably enough, isn't it? But I would recommend that you look at the practice exams and get comfortable with that material. A, B, C, and D are probably in chapter 10. But the last section of chapter 1, section 10 of chapter 1, talks about these equations. So if you can put these equations together, that's what I'm looking for. Pardon? MATLAB won't really be prominent on the exam. What you've done so far in MATLAB, I don't really want to ask you a question to do that on the exam, but what you need to be thinking about is, how do I simulate something in MATLAB as far as how long do I need to simulate, that's my time horizon, and how fine do I chop it up. We'll get to that later. That's not a part of this exam either, but you've started to do that with your simulations in MATLAB already. I do have office hours tomorrow morning and Thursday morning, and I will definitely see you on Thursday at whatever time the class starts, 12:30.